Hi guys, welcome back to my channel. It's the educator here, and this is going to be the first video I'm going to be uploading under the PHY111 series. Okay, so I started this series just in case you don't know for 100 level students, especially those in their second semester. And then in this series, I've outlined 5 courses that I'm going to be doing tutorials on, video tutorials basically. And these courses include PHY, that's physics, zoology, biology, chemistry, and then mathematics. All right, so if you are just turning into this channel and this is the first video that you are watching this channel, please do want to hit the subscribe button if you love something like this, so that when I upload videos, you are not going to miss out. Just in case you don't know, I've also uploaded videos for chemistry, mathematics, and biology. So just do want to check out my channel and then watch the video. Alright, so let's dive into today's video. So for PHY111, which is the second semester course, the concentration is electricity and magnetism. So everything that we're going to be doing under this series is going to be electricity and then magnetism. Alright, so let's dive into today's lesson. So today's lesson has been divided into 4 parts, right? 4 parts, and then we'll be taking the 4 parts step by step while we go through this lesson. All right, so for the first part, we'll be looking at electrostatics. Okay, so now under electrostatics, the topic will be concentrating on our forces in nature and then the concept of charge. Let me look at forces in nature. What exactly are we talking about when we say forces in nature? All right, one thing you should take note of is that they are fundamental forces. There's a terminology, or there's a class of force known as fundamental forces. Right? When we say something is fundamental, it means that it cannot be done without. So everything we are going to do, basically everything that happens around you, all the interactions around you are governed by these 4 fundamental interactions or 4 fundamental forces. And they include these 4 which I have outlined here, which includes gravitational force. So gravitational force basically is the attraction between masses. So when you hear mass 1, mass 2, a distance, just know what they are talking about is gravitational force, right? Another force we have is weak nuclear force. So when we look at weak nuclear force governs radioactive decay. So in radioactivity, though we are going to look at that in chemistry, in radioactivity decay, there is a force there. That force is the weak nuclear force. Please take note of that. And then we have the electromagnetic force, which is going to be our concentration for physics 111. Okay, because we did something relating to gravitational force in first semester, right? But for this semester, we're looking at electricity and magnetism. And under electricity and magnetism, the force we'll be concentrating on is the electromagnetic force. So this basically includes force, the force between charged particles. Okay, so when a particle is charged, when 2 particles are charged, there's a force that there's an interaction between these 2 charges, and this interaction is known as the electromagnetic force. And then we have the last one, which is a strong nuclear force. So remember, we have weak nuclear force, and then we have strong nuclear force. Right. So for strong nuclear force holds the atomic nucleus together. You should know that weak nuclear force governs radioactivity, while the strong nuclear force holds atomic nucleus together. All right. So moving on, next thing we'll be looking at is electric charge. Electric charge. Now, for electric charge is indicated with the alphabet Q. Right. So when you hear electric charge, or when you see this alphabet here, small letter Q, you know what they are talking about is electric charge. So basically, what's charge? Charge is a fundamental property of matter that causes it to experience force in an electromagnetic field. So basically, if a particular material, so let me say there's a particular material A, and then there's another particular material B. Now, when this material is placed in an electromagnetic field, okay, so let me use another color to represent electromagnetic field. So let me say they are placed in electromagnetic field. This green represents the electromagnetic field. Now, there's something that happens if there is a charge in A, right? So let me use another color to represent the charge. So if there's a charge in A, let me say these are the charges in A, and then these are the charges in B. We don't know the charge, either positive or negative, right? Now, there's going to be an interaction between these objects, or between this matter and then the electromagnetic field. But now, what is making it to have this interaction? What is making it to have the interaction is the charge that is present. That is the one represented with purple. That is what is making it to have interaction, which means that if a particular matter does not have a charge, it is not going to experience any force in an electromagnetic field. So take note. So in an electromagnetic field, a matter that does not have a charge will not experience any force. So this boils down to the types of charge that we have. We have positive charge, and then we have negative charge, right? So for positive charge, we experience a force. Negative charge will experience a force. But then if it is neutral, there will be no force. Okay, so please take note of that. All right. So another thing we're looking at is the quantization. So for the quantization, one thing we should take note of is that charges exist in discrete packets, right? So the smallest unit of the charge of an electron is represented with the next slide that I'm going to be showing you. Now, this is the smallest All right, let's go back to the previous slide. So the previous slide here says the smallest unit is the charge of an electron. The charge of an electron is the smallest unit. So basically, what is the charge of an electron? That is what is represented in the next slide. So this is the charge of an electron. Now, total charge is given with the formula Q is equals to NE, where N is any integer, right? N can be an integer. E represents the electrons, and this is the constant for this electron. We have 1.602 times 10 raised to power minus 19 coulombs. Okay, so please take note of all these constants. Right, so just in case you are wondering that, oh, this slide I am using to do this lesson is concise and it's easy and very understandable, this slide is from the material which I recently made. Okay, so I'm going to be dropping access in case you want and you're interested in this material. All right, so this material is going to be giving out on sales, and right now we have a bonus price. Okay, so if you want to access the material right away, you just need about 1,999 naira to access the material. After which, on the 20th of May, the material is going to be for 4,000 naira. So if you are not having access to the material now, then in few days time you might not be able to access the material with that price. Okay, the material has a lot of things inside. You have the notes to past question, from past question to worked examples. All right, so you have everything in the material. All you just need to do is to indicate your interest in the comment section. If you're interested in the material, just indicate it in the comment section. But then I'm going to be dropping the link for you to have access to the material in the description box or in the comment section. So just do well to check it out. All right, so let's continue the lesson. Okay, so the next thing we're looking at is Coulomb's law. Coulomb's law. So basically, what exactly is Coulomb's law? Coulomb's law, this law quantifies the force between two stationary points. The force between two stationary points. All right, so what does the law say? The law states that the magnitude of an electric force, between 2 point charges. Remember, we said that the force between two charges is electromagnetic, right? Please don't forget that. And now there's a law trying to prove this interaction, and this law is the Coulomb's law. Coulomb's law. So Coulomb's law is stating that the magnitude of electrostatic force between 2 point charges is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. Now, if you should look at this law, you see that this law is kind of similar with the Newton's law of gravitation, right? The Newton's law of gravitation states that the force between two masses is directly proportional to the product of the masses and then inversely proportional to the square of the distance. All right, so remember that gravitational force is between two masses, while electromagnetic force is between two charges, and that's what differentiates the law. Okay, so if we should break down this law, what this law is saying is that the force is directly proportional to what Q1, and then we have Q2. That's directly proportional, and inversely proportional to the distance r. R is represented as distance, the square of the distance, right? By the time we add the constants to this, we'll be having something like this: F, that the force, is equals to K, which is the constants, right? Q1, and then we have Q2, product of the charges, and then we have R square, the distance, square of the distance, right? Now, Coulomb's constant, this K here, Coulomb's constant, is approximately 8.99 times 10 raised to power 9 Newton per Newton meter square per Coulomb square. Please take note of this. It is very, very important for you to take note of all these constants. So I've mentioned two constants in course of this lecture. The first one was the one related to electron, and now the second one we're mentioning is the Coulomb's constant. Please take note of all these constants. They are very, very important. So just in case you might be wondering, how did we manage to get this Newton meter square per Coulomb square? It is very, very easy. Now, if you should find the subject formula of K, the subject formula of K is going to give us F R square. If you did your mathematics very well, F R square divided by Q1 over Q2, right? Q1 over Q2. What is F? F is Newton. So we have Newton. R distance is what? Meter, right? We have meter square. And then the charge. The charge is represented as what? C, right? Coulomb. Coulomb square. Coulomb square. And so that is why we have this Newton meter square per Coulomb square. All right, so moving on, we have the permittivity of free space. So permittivity of free space is another concept that we are going to be looking at. So under permittivity of free space, what exactly is permittivity of free space? So permittivity of free space is a constant. What exactly is this constant? So Coulomb's constant, remember Coulomb's constant is key, right? Coulomb's constant is key. And then Coulomb's constant is related to this permittivity of free space, which is represented as this E, then subscript O, subscript 0. So what exactly is the relationship between Coulomb's constant and permittivity of free space? The relationship is K is equal to 1 over 4 pi, the permittivity of free space. So the constant K is equals to 1 over 4 pi, then permittivity of free space. Please don't mind me the way I wrote my E, but then you can still write it down, but please don't mind me. Now, this E naught is represented, or this E naught has a constant which is 8.854 times 10 raised to power minus 12 Coulomb square divided by Newton meter square. So please take note of this. So we have three constants now, right? We have the one relating to the charge, we have the one relating to Coulomb's, that's Coulomb's constants, and then we're having another one here, permittivity of free space. But now, the reason why we are getting permittivity of free space is because we have Coulomb's constant, right? So we have Coulomb's constant, and Coulomb's constant is giving us the permittivity of free space. All right, so moving on to the part two of this module, electrostatics. And so for the part two, we'll be looking at electric field, potential, and superposition. Now, in this particular lesson, I have made it much more easier in the sense that for all the quantities and all the concepts that we'll be looking at, I have outlined them to be either vector or scalar quantity. So if you see vector beside one, you know that that quantity is vector, because your exam will come in that pattern. They will assume that you should know vector and scalar. So they might not really tell you that, oh, this is scalar, oh, this is vector, but then you should have it at the back of your mind. All right, so the first thing we're looking at here is electric field intensity, which is represented as capital letter E. So the electric field is the space around the charge where its influence can be felt by other charges. Okay, so the electric field is the space around a charge where its influence can be felt by other charges. Okay, so for definition, the electrostatic force per unit positive charge, positive test charge. What this means is that if we were to define it based on the formula, this is how we are going to define the electrostatic force per unit positive test charge. What does this mean? We have E is equals to electrostatic force divided by, when you see per in physics, you know it is divided, right? So per positive test charge, and remember that Q is for your charge. All right, so let's move on. So one thing you should take note, or one thing you should take note of in this particular session is that electric field intensity is a vector, right? And it's represented with this formula, electrostatic force divided by positive test charge. The reason I'm giving this formula is so that when you are presented with questions, for example, they give you a question and they give you the positive charge and they give you electrostatic field and they tell you find the electric field intensity, you should know what to do. You should know that electric field intensity is the force divided by positive charge. Okay, so let's move on. So we'll have that the unit is Newton per Coulomb or V per M. Right, so moving on, the direction, point away from positive charges and towards negative charges. So what happens is that for the electric field intensity, it points away from positive charge towards the negative charges. Okay, so take note of that. So it means that if this is positive charge and negative charge, the electric field intensity goes from the positive towards the negative charges. All right, so please take note. Then moving on, the next concept we are going to be looking at is the principle of superposition. The principle of superposition. So when multiple charges are involved, the total field at a point is the vector sum of individual fields. That is just basically what principle of superposition means. When multiple charges are involved, remember we'll be looking at charges, one charge at a time. If you look at this formula, the electric field intensity, it is just relating to the electrostatic force and then just one charge, right? But now when we look at the principle of superposition, it is when multiple charges are involved. So when multiple charges are involved, what should come to your mind is principle of superposition. And what does this principle state? This principle states that when multiple charges are involved, then the total field at the point is the vector sum of the individual fields. So let's move on, then you understand what I'm talking about. So this is what I'm talking about here. You can see the total field, which is the E net, is the vector sum of the individual fields, right? Look at it here. The vector sum of individual fields. Okay, so field 1 plus field 2 plus field 3, and just consider like that, depending on the number of fields that are presented, it will give you the total field. All right, so you must resolve vectors. Now, what you should take note of is that you must resolve vectors into components x and y before adding them. Please take note of that. You must resolve vectors into x and y. All right, that is why physics is progressive. In first semester, you were taught how to resolve vectors into x and y components. You were taught vectors, and this semester nobody is going to go back to teach you vector. So you should know how to resolve vector into components x and y before you add them. Okay, magnitude alone is not enough. All right, so moving on, we have the electric potential. V, electric potential V. So we have looked at three things now. The first one is the electric field intensity, and electric field intensity is E, and it is a vector, right? And then we have looked at principle of superposition when we have multiple charges involved. When multiple charges are involved, we add the field together to give us the total field. Okay, and that's the formula there. And then we have electric potential V. Electric potential V. When you see V anywhere in physics, you should know V is electric potential. Okay, so this is a scalar quantity. Take note, this scalar quantity. What exactly is electric potential? Electric potential describes the energy environment without needing direction. Okay, so what is the definition based on the formula? Right, physics is easy because you can define quantities based on formula. So you know the formula and then you also know the definition. All right, so what is electric potential based on formula? Electric potential based on formula is the work done per unit charge in bringing a positive test charge from infinity to a point. From positive charge, bringing a positive charge from infinity to a point. That is what your electric potential is. And this is the formula for electric potential. Formula for electric potential is Q over R. Remember, Q is our work done. That is Q. And then R is what? R is going to be your distance. Please take note of that. Okay. All right. So the fourth concept we're looking at is electric potential energy. And electric potential energy is represented with U, represented with the sign U. So total energy stored in a system of charges is the electric potential energy. That's the total energy. And then this is what it is represented as. It is a little bit similar with Coulomb's law equation, but the only thing is that it is not R square, it is just R. So please take note of that. So the crucial rule is unlike the force or field formulas, we keep the negative sign of the charge in this calculation. So if we're solving for force and field using the force and field formula, we'll neglect negative charge. But in this particular equation, in this particular formula, negative charge is retained while the calculation is carried on. All right, so moving to the part 3. Okay, so for the part 3, we'll be looking at the Gauss law and electric dipoles. Now, just in case you might be wondering that, oh, why is there no calculation or why is there no examples and stuff like that? So this video I am making is just to explain the key concepts under all of these topics, give you their formula, tell you possible questions, tell you how the exam is going to be set. Okay, if you want to see examples, worked examples with a lot of questions that you can use to practice, please I advise that you do well to check out that material I have created. Okay, the material is quite affordable right now, selling for the price of 1,999 naira. In a few days' time, it's going to go back to the original price, which is 4,000 naira. So if you are watching this video now, it's an opportunity for you to get the material right away. I'm going to drop the link, like I said. All you need to do is to click the link and make payment, and then you access the material right away. Okay, so for Gauss law and electric dipoles, we'll be looking at electric flux first, and this is the representation for electric flux. Okay, so electric flux measures the total number of electric field lines passing through a given surface area, and so this is the formula. Electric flux is E times A times cos theta. Okay, electric field, that's A area, and then you'll be given an angle, definitely that's theta, so you have cos theta. Okay, so electric flux, you should know that electric flux is the electric field times the surface area times cos theta. Please take note of that. Now for the keynotes, one thing you should take note of is flux is maximum when the field is perpendicular to the surface. When they say something is perpendicular, it means that the angle is zero. The angle is 0 degree. So you will see a question and it will tell you electric flux is maximum when theta is dash. Just know it is when theta is what? Is zero. And then electric flux is now zero when the electric field is parallel, which means that the theta here is 90. So this question, from this keynote, you can bring about 4 to 5 different questions. And so these keynotes here, all the keynotes that I will be dropping in this lesson, please take notes of them because they form the theoretical aspects for your physics examination. Okay. So for the Gauss law provides a shortcut for calculating electric fields of symmetric charge distribution. So we have spheres, cylinders, etc. The net electric flux through any closed Gaussian surface is equal to the net charge enclosed divided by E0. You should remember what E0 is now, permittivity of space. Permittivity of space. So this is the formula So Gauss law basically is just a shortcut. Okay, it provides a shortcut for you to calculate electric field, and then this is the formula here. This is the formula. You have your electric field, then you have your area, surface area, then you have your charge when it is enclosed, when it is an enclosed Gaussian surface, and then you have E0 to be your permittivity of space. All right. So why use it? Why use it? You might see a question like that. Why do we make use of the Gauss equation or the Gauss law? It is much easier than Coulomb's law for calculating the field around a charged wire or a large flat plate. Please take note of that. All right. So for the electric dipoles, a dipole consists of two equal and opposite charges separated by a distance. So what exactly is a dipole? A dipole consists of two equal and opposite charges. So if we have a charge here, then we have another charge here. So we have this charge here to be plus and this charge here to be minus. And then there's a distance between the positive and the negative charge. So what happens here is that when the charges are equal, and then the charges are opposites, and they are separated by distance, then this whole system here is known as a dipole, an electric dipole. Alright, so dipole moment is represented as P. P. Alright, it is a vector pointing from the negative to the positive. And the torque represented as T, not necessarily T, but then it looks like small letter T. So when it is placed in an external field, dipole feels a turning force, and this is the formula. So you have P, which is dipole moment, times the external field E. Please take note of that. Or when you are given an angle, you use the dipole moment times the external field sine the angle that you are given. All right, and you should also take note of this formula. You have P, which is the dipole moment, is equals to the charge Q times the distance D. Okay, let's take note of that. So for conductors and insulators is a very common concept in physics. It's not new to you guys. It's a common concept. When we hear conductors, things that allow electricity to pass through them or conduct electricity, right? So conductors are materials where charges move freely. Now, in case they ask you why do conductors conduct electricity, because they have charges moving in them freely, all right? Then insulators, they do not allow easy charge movement. All right, so take note of that. All right, so this is going to be the last part in the electrostatics lesson series. And this part will be looking at capacitance and electric energy. Okay, so basically what's capacitance? One thing you take note of is that a capacitor, firstly, is a device used to store electric charge. So that can be another question. To ask a device used to store electric charge known as what is a capacitor. And then the electric potential energy. Okay, so definition of capacitance now. So the ratio of the magnitude of charge on either conductor to the potential difference between them is known as capacitance. So this gives us a clue that capacitance Q, or C rather, is equals to Q divided by V. Right, so this is the formula. C is equals to Q divided by V. I know this particular aspect of the lesson is a bit relatable compared to others, and that is just the way it is. Okay, so just all right, so this is the formula just I have indicated in the previous slide. So F, the farad. So capacitance has the unit farad. And take note that 1 farad is very large, so we don't really use farad in calculations, right? So what we use in calculation is the pinofarad. That's this farad, nanofarad, or this farad. So so that's why you see in calculation, you have to do multiply by times 10 raised to the power minus 6 or times 10 raised to the power minus 12. All right, so moving on, we have parallel plate capacitor. So parallel plate capacitor for two plates of area separated by distance. That is what we mean by a parallel plate capacitor. And then it's represented with the formula that you can see here. And so this formula is remember that this is the capacitance. And then you have this E naught to be the permittivity of space. Then you have A to be your area, and then you have D to be your distance. So this is the formula when we have the parallel plate capacitors, right? So yes, moving on. Dielectrics. So dielectrics, if an insulating material is known as a dielectric. And so it has a constant K is inserted, the capacitance increases. Basically, this is another note and then it forms another theoretical part of your exam. They'll just ask you if an insulating material with a constant K is inserted, what happens? Will the capacitance increase? Will the capacitance decrease? Will the capacitance be zero? Or you should know that the capacitance increases. Okay. So energy stored in a capacitor. Energy stored in a capacitor. Capacitance, we already know what capacitance is. So now what is energy stored in a capacitor? Energy stored in a capacitor is represented with U. And then we have the formula half CV square. Half CV square. Half CV square. So just remember CV, we are going to look for a job, CV square. We are going to look for a job, CV square. Right? So this is the formula for energy stored in a capacitor. Right? But now you might not be wondering, how did we now get this one? How did we get this one? It is very simple. Now remember we said that if we go back to the previous slide, we said that C is equals to Q over V, right? That's capacitance. C is equals to Q over V, right? So if we insert Q over V into this particular equation that you are seeing here, that's this C now becomes Q over V. We'll be having something like Q V, half QV, right? Half QV. Now, what is Q? That's another thing that we'll consider. What is Q? Q is CV. By the time we do Q, it's going to be CV. If you replace Q with CV, right, we are still going to come back with half CV square. It's as simple as that. The same thing if you find V. What exactly is V? V is going to be Q over C, right? Q over C. So if we replace this V here with Q over C, we'll now have something like half Q square over V. Over C, sorry. So that's we are going to have Q square over 2C. So the reason for this subject or formula is because in some questions, they might give you just capacitance and then they'll give you the potential difference and they'll say find the energy stored. Or they'll give you charge, they'll give you just like that, they'll just mix it. So you should know the appropriate formula to use at the right time, depending on the question that you are given. Alright, so moving on, we have combination of capacitors. Combination of capacitors. These are another very common concept in your physics. So we have the parallel combination and then we have the series combination. So for the parallel combination, something you should take note of is that the voltage is the same across each capacitor, while the charge is the same for series. Right? Voltage is the same here for capacitor, charge is the same for series. Now this points us to why. Remember we have that Q is equals to, or C, let's use C. C is equals to Q over V, right? Q over V. So now, if voltage is the same across each, it means that this voltage here, we're not using it, right? So it's not like we're not using it, but that's just a shortcut for you to know. So we have Q. So because of that, it is straight. So we have C1 plus C2 plus C3 because of this guy. Q is equals to C is equals to Q since we're not using V. Please take note of that. So it's going to be straight. That's why we have C1 plus C2 plus C3. Now for this, charge is the same. So using the same formula, C is equals to Q over V. If they say charge is the same, that means we're going to cancel this Q, right? If we cancel this Q, we have C is equals to 1 over V, right? 1 over V. Remember that we're not writing V, or we're not writing the formula as 1 over V1 plus 1 over V2, 1 over V3, just like that. We're just using it as a shortcut for you to remember, oh, in parallel, it's like this, in series, it's like this. But then if you know it right from your secondary school days, then you might not find this mnemonic or shortcut really helpful. But then you should take note that parallel combination, voltage is the same, series combination, the charge is the same. Okay, and then so we'll come to the end of this lesson in this series. Okay, so stay tuned and ensure that you have subscribed to my channel so that you don't miss out on any video that I'm going to be uploading subsequently. Ensure that you share this video to your friends, share this video to your department, share this video to your group chat and then your status. Ensure you indicate in the comment section if there's any concepts stated in this video that you don't understand, so that I'm going to make subsequent videos to break it down for you. And as usual, please don't forget to purchase the material. I'm going to drop the link in the description of this video. So do have to check the description of the video and then click the link to purchase your material right away. See you guys in the next video.